All right, everybody. So this is going to be part two of the section 10.2 lecture. I'm just going to write the notes in the same document that we used last time. So there'll just be one set of notes for this. So what did we do last time? Just a quick recap here. So we talked about some definitions for graphs. We talked about neighbors, which meant that two vertices were next to each other, then they were neighbors. We talked about incidence, which was kind of the same concept, but for edges. An edge, like this one right here, is incident with these two vertices. So an edge is incident with whatever vertices it is between. You can have a neighborhood, which is all of the vertices that are adjacent to a particular vertex. So you can say like the neighborhood of V3 is V2 and V4, because on the graph, V2 is here. Wait, no, V3 is here, and it's adjacent to V3 and V4. They're right here. And so on. So we had some stuff. I'm not going to go over this, but we had a theorem that related the degrees of the vertices to the number of edges, which in this case was 6. So 6 edges, and if you add up the degrees, it was 12, because that number is double of that number. Yeah, and that's pretty much all we did. So let's go ahead and pick up there and talk about what we need to do next. So let's see here. So we're going to talk about directed graphs a little bit. Directed graphs. So we're going to have a few of the same kind of definitions. So when UV is an edge, so from U to V, with is an edge in G with directed edges. U is said to be adjacent to V, and V is said to be adjacent from U. So you can see what they're doing, right? Adjacent to and adjacent from. So the idea is, the edge goes from one vertex to another vertex. So there you go. Adjacent, where are we? Adjacent from U. So U is called the initial vertex. Of UV. And V is called the terminal vertex. Right? And so just so we're clear, U, V, and the arrow goes that way. Right? So you've got initial, terminal. We can even write that in. Initial, terminal. All right. And so there we go. Now we can talk about the degree, because when we talked about degree before, we talked about only the degrees of undirected graphs. So we didn't talk about directed graphs. So degree of a vertex in a directed graph. All right. So that's what we want to talk about. Turn that into a box. Thank you. All right. So what is it? Well, here it is. So definition. So the in degree of vertex V, which you write this way, DEG with a minus sign, is the number of edges uh, where V is a terminal side or terminal vertex, sorry. Right. So in degree, it means the number of edges coming in. So, right, like this right here, it comes into V. So V has an in degree of 1, and U has an out degree of 1, which we haven't defined, but you can figure it out. So in degree, number of edges where V is a terminal vertex. So those are edges coming in. And out degree, the out degree of V, which is going to be DEG plus, is the number of edges with V as the initial vertex. Right, so let's do an example. V1, V2, V3. So if this is what we have, then we could talk about the in degree and out degree for each of these. So let's do the in degree for each of them. Or let's do in degree, out degree. So if we do the degree in for V1, degree in for V2, degree in for V3, degree out 1, degree out V2, degree out V3. All right, so we're just counting here again, degrees in and out. So looking at V here, V1, sorry, the degree in is the number of edges where V is the terminal vertex. So you say, okay, how many edges are coming into V1? Well, this one is, and this one is. So 2 edges are coming into V1. So this is 2, right? And if you say how many edges are leaving V1, then there's just 1, right? This one right here goes to V2. So the out degree is 1. And these add up, right? 2 and 1 to, there's actually 3 edges right here. Okay, so let's look at degree V2. So we got V2 here. That this is out, this is out, this is in. So there's 1 coming in and 2 coming out. So 1 coming in, 2 coming out. Then we get to V3. V3 has 1 coming in and 1 coming out. So 1 and 1. And there you go, in degree and out degree. Now, the relationship between the degree and the edges is a little bit different than the one we learned up here in the previous section, right? So the theorem up here said, wherever it is, yeah. This said, if you add up the degrees, you get 2 times the number of edges. Well, what's going to happen here is theorem is, let's see, let G equal VE, just a graph with directed edges. So if you add up, if you add up the in degree, that's going to be equal to if you add up the out degree, right? Like if you just add these numbers, 2 plus 1 plus 1 is 4, 1 plus 2 plus 1 is 4. So both 4. So those are equal, and they're both equal to the number of edges. And so the way they wrote this is this is cardinality, which we learned about, of the set of edges. So the number of edges. Okay, so there you go. That's the relationship for directed graphs. Okay, so now let's look at some simple graphs. Special graphs, I guess we could call them. Special, simple graphs. Right, so these are graphs that have names, and so people refer to them and they expect you to know what they look like. So these are common graphs that happen to have names. All right, so let's look at them. So there's a complete graph. Complete graph within vertices. So this is so it's called Kn, and then what it is it's one edge between every pair of vertices. One edge between every pair of vertices. So K1 is very simple. It's just a dot. I mean, just a single vertex. K2 is two vertices, and then basically you just connect them because every pair of vertices has an edge. K3 has three vertices. And again, what you do is you just put an edge between every pair. So edge there, edge there, edge there. That's K3. K4. So a pair, like an edge between every pair of vertices. So this vertex here is connected. Oh, you can't see. This vertex here is connected to all of the other three. So there, there, there. And then that's true for all of them. So like that. So there's no edges, like there's no vertices that are not adjacent. Every vertex is adjacent to every other vertex. Okay, draw one more. And I think you'll get the idea. So K5 has five vertices, and so every vertex is connected to every other vertex. So you have to put in every single possible edge. And there you go. So that's the complete graph. Kn. Okay. Well, that's one of them. We can do another one. So cycle. Which we call Cn. So this is going to be with n greater than 3. So n greater than 3 vertices. N1, nope, already messed up. V1, V2, V3. So we're going to name them here. So there's V1 through Vn vertices. And then what you do is there's edges between V1 and V2, and then V2 and V3, and so on. So so there's edge with edges. And so the edges are, how are they writing them? They're writing them like this. V1, V2. I don't know why they're using curly braces when they used parentheses before, but V1, V2, V2, V3, V3, V4. See the pattern? And you keep doing that, right? And you're going to get up to the end. Eventually, you're going to get to Vn minus 1, Vn, And when you get to v in minus 1 vn, there's one more, which is vn connects back to v1. Okay, it's not as complicated as it sounds. Right, the idea is you go from v1 to v2, v2 to v3, and then when you get to the end, you go back to the beginning. Same thing here, v1, v2, v3, v4. You go v1 to v2, v2 to v3, v3 to v4, v4 back to v1. So that's C4, cycle. Now, C3 looks exactly like K3, right? C3 and K3 here, C3, K3, identical. C4, K4 are not identical because we have these crosses here, but we don't have that on C4. C5, I'm not going to draw in the letters this time, or the vertex names. I mean, hopefully you saw the idea, right? It's called a cycle. It just goes around in a circle, basically. And these keep going, right? You can go C6, C7, C8, and so on. All right. Wheels. Wheel, Wn. So this is an interesting one. So cycle, like Cn, n is the number of vertices, right? And on the complete graph, Kn, k is the number of vertices. On the wheel, it's not. And that's kind of, I don't know, weird notation, but you'll see kind of makes sense. So wheel, Wn. So what you do is you take the cycle Cn, add one vertex, and connect, and add one edge between the new vertex and each of the vertices of Cn. So W3, for example, looks like this. So for W3, you start with the cycle, and then what you do is you add one new vertex, which we draw in the middle, and then that vertex gets connected to the vertices in the cycle. And the idea is that it's called a wheel because what you're doing is you're taking a cycle and you're making it a wheel by adding some spokes, like a center and some spokes. So it looks like a wheel. That's the idea. So we got these other two, right? We got, let's see, just duplicating this. You can't see it, but now you can. So we have these, erase that, erase that. So if we want to turn this into W4, you just add center vertex and then connect that to the outside. Here we want W5, so we take C5, add a center vertex, and connect that to the outside vertices, and so on. And those are wheels. All right. Now we got cubes, hypercubes, or n-dimensional hypercubes. Qn. All right. So this is going to be a little bit confusing, but the idea is Um, so the number of vertices is going to be 2 to the n, I think. Yeah. So Qn has 2 to the n vertices. Okay. You label each vertex with the n-digit binary number, with an n-digit binary number. This is confusing, I know, but it'll make more sense when we see it. Trust me. N-bit binary number assigned to it. I should say a different n-bit binary number assigned to it. And then the edges between vertices, there is an edge between vertices if their binary numbers differ in exactly one place. All right, that's the definition. So, I mean, this is very complicated, and you're going to be like, okay, well, how do you even go about drawing it? So here's how you go about drawing it. Q1. So Q1. So what you're supposed to have is 2 vertices. Why 2 vertices? Because 2 to the n vertices, right? So if n is 1, there should be 2 to the 1 vertices. Then what you do is each vertex has a different n-bit binary number. So 1-bit binary number. So this one must be 0 and this one must be 1, right? They're 1-digit binary numbers. We're using zeros and ones. Okay. And then there is an edge between vertices if their binary numbers differ in exactly one place. Well, yeah, there is only one place, right? This one's a 0, this one's a 1. So they differ in one place. 0 and 1 are different. So there should be an edge. So there you go. That's a one-dimensional cube. Not that interesting. Q2. So Q2 is where you can actually start to see the pattern starting to take place. So again, you number these with binary numbers, and there's like a lot of different ways to do it. I'll call this one, so 2-digit binary numbers. So we'll go 0, 0, 0, 1, 1, 0, 1, 1. And I'm just putting these in the same order that they are in the book because, I don't want to draw a weird picture here. So I want to make sure I draw the same picture. So, right, we're doing 2-digit binary numbers. So you just put a 2-digit binary number on each of your vertices. There's 4 because this is a 2, and 2 to the 2 would be 4. So 4 vertices. All right. Then what you do is you connect the vertices where they differ in one place. So what that means is like 0, 0, 0, 1. The zeros match, but the second 0, we have a 0 and a 1. So they differ in one place, right? This is a 1, this is a 0. So you put an edge. Okay. Now look at this, 0, 0, 1, 1. You don't put an edge here because 0, 0, 1, 1, these differ in 2 places, right? 0, 1, 0, 1. So they differ in 2 places. So no edge here. Okay. Now here, 0, 1, 1, 1. The 1 and the 0 don't match. The 1 and the 1 do match. So they differ in one place. So that gets an edge. 1, 1, 1, 0. Those differ in the second place. So one place. Here, 1, 0, 0, 1. They differ in the first place. So there you go. If you look, there are no other edges that you should draw. So that's Q2. So that's a two-dimensional cube or square, right? Two-dimensional cube is a square. Two-dim cube is a square. All right. Now, then you've got the next one. Now, I'm going to show you an easy way to draw these. And then we'll actually put the labels on it. So if you want to draw Q3, which is actually going to be a cube, what you do is you kind of draw two copies of Q2. And then what you do is you connect corresponding vertices with edges. And you're able to draw this one still using the pattern that we have talked about, or using the definition, but I'm writing these rules because it'll be easier to draw Q4 this way. So what I mean by this is you draw Q2. There's Q2, right? And then you draw another Q2, which, usually people draw it right here. Like that. So that's two copies of Q2. And then the edges that you add in, are between corresponding vertices. Corresponding vertices mean like this. Like we've got top left, connect those. Top right, connect those. Bottom right, connect those. Bottom left, connect those. And you get a three-dimensional cube, which is actually a cube. Looks like a cube. Now, of course, we could have followed the method that they actually described in the definition, which would have looked like this: 0, 0, 0. We're at three-digit numbers. 0, 0, 1, 1, 0, 1, 1, 0, 0. That's the front cube, and then the back cube is 1, 1, 0, 1, 1, 1, 0, 1, 1, and 0, 1, 0. So yeah, three-dimensional cube. And if you needed to draw Q4, which they don't draw Q4 in the book, and you can probably imagine why they don't draw Q4 in the book, because it's going to be a pain to draw. But if you're trying to draw Q4, what you would do is the exact same thing. I draw Q. I'm going to erase these numbers here. Oops. Sorry. All right. Connect. So if you're trying to draw Q4, what you would do is you would draw Q3 like I did. You draw a second copy of Q3 like that. And then again, you have to connect all of the corresponding vertices. So like back top left, back top right. And you do that for all 8 vertices. So like bottom left in the back. Same thing for the right. Okay, so that's the back one. Then you got to do all the ones in the front. Okay, there you go. So this would be Q4. So you can see why they don't draw it in the book. But if you ever need to draw it, then this is the pattern that I would follow. You can follow basically these directions here to get from one hypercube to the next up hypercube. Anyway, interesting. So hypercubes, n-dimensional hypercubes. Obviously, Q2 and Q3 are the ones they use a lot. Q4 they don't use a lot because they're a pain to draw. It's hard to draw a 4-dimensional shape on two-dimensional paper. Okay. So now what we want is we want to have something pretty important called bipartite graphs. So we're done with the special graphs, but we're going to talk about bipartite graphs. There's usually a test question on bipartite graphs, so hopefully we'll learn this pretty well. So here's a definition. A simple graph is bipartite if it can be partitioned, if the vertex set V can be partitioned into two sets, V1 and V2, so that all edges go from a vertex in V1 to a vertex in V2. Okay. So what that means basically is no edges from V1 to V1, that kind of thing. So that's the definition of a bipartite graph. What do they look like? So a bipartite graphs usually are drawn like this. So example, this is just a bipartite graph. So often they'll draw them with vertices on the left and other vertices on the right. And the idea is all the edges go from left to right. They don't go on one side. So like V1 is here and V2 is here. So like you can have that edge, this edge is allowed. This edge is allowed. This edge is allowed. There's more edges allowed, but the point is that for every edge, one side's on the left and one side's on the right. On the left, one on the right. One on the left, one on the right. There's none going between these edges, and there's none going between these edges. So those are bipartite. So let's draw another one. So there are others that are bipartite. So like if I draw, hold on. Like if you draw C4, this is C4, right? Now C4 is bipartite, I think. We're gonna draw it real quick. Is bipartite because you can just move the vertices around, keep the edges, and you can make it look different. You could draw a different picture. So like we know that the vertices are called V1, V2, V3, V4, right? Well, what if you just draw them like this? What if you put V1 here and you put V3 here, and over here you put V2 and V4? Then what you've got for your edges is you've got an edge from V1 to V2. That didn't do what I wanted. An edge from V1 to V2. Then you've got V2 to V3. Then you've got V3 to V4. And then you've got V4 to V1. And so look at that. All the edges are from left to right. They don't go, there's none between here. There's none between here. So that's bipartite. So it didn't look bipartite, but you can redraw it and it looks bipartite. So you have to be careful. Like the definition tells you if it's bipartite, not the picture. Yeah, not the picture. Now there is a nice theorem though for actually for showing that two graphs are bipartite. So this is important to know. So to check if two graphs, or not two graphs, to check if a graph is bipartite. Come on, erase. You don't want to have to, you could redraw it like this, like from here, you could try to redraw it like this, but you don't really want to have to do that. So you don't really want to have to draw a new picture. So if you want to check if a graph is bipartite, you can use this theorem. So this theorem says, this is theorem 4, I guess. It says a simple graph is bipartite if and only if and only if it is possible to assign two different colors, possible to assign one of two different colors to each vertex so that no two adjacent vertices have the same color. Okay, so let's see here. One moment. Yeah, so like as an example, let's get this one from the book, maybe. So I'm just going to try to draw this. Almost done. Oops. Come on, stop. Why are you doing this? Okay, I think that's right. Okay, so here's a graph, and we want to know if it's bipartite. And so you could, try to redraw it, but it's hard to redraw it. Like I didn't put labels on any of the vertices, so you'd have to maybe name them or number them, and then it could be hard. So the easiest way to do this is using this theorem here, which says you just pick two different colors and we just start calling the vertices by that color. So like if I pick yellow and pink, I'm just going to use a highlighter here. Like if I call this one yellow, then the next, anything that it's adjacent to has to be pink. So if that one's yellow, then this one over here must be pink, right? Because there's an edge. And also this is adjacent to this one and to this one. So this one must be pink and this one must be pink. So you go pink, pink. All right, then for each of those, you do the same thing. We're going to have some more yellow. So this one is pink. So that means this one needs to be yellow. This one needs to be yellow. Yellow, yellow. Okay. And you just keep following this pattern. Let's go to one of the other pink ones. So this pink one here, this one's yellow. This one's yellow. That's it. It's only connected to those. So that's done. This one here, this one's yellow. This one's yellow. This one's yellow. All right. Um, oh, we missed one, huh? This one, pink. We did pink, pink, pink. We didn't make this one pink. Pink. All right. So if you look at that, you can just color them this way. You start anywhere and then pick a color. And then you look to see, well, do we have any pink adjacent to pink? Or do we have any yellow adjacent to yellow? And I don't think we do, right? Yellow, pink, yellow, pink, yellow, pink, pink, yellow, yellow, pink, pink, yellow, pink, yellow, right? It looks fine, right? No pink is adjacent to any yellow, right? So we colored them. And no pink vertex is adjacent to a yellow vertex. That means G is bipartite. So that's the easiest way to do it. And that's how like if you wanted to know if C4 was bipartite, then you do it the same way, right? You say that's pink, so that's yellow, so that's pink, so that's yellow. Okay, right? And if you've got it drawn in this form, then it's like yellow, yellow, pink, pink, pink. So if you've got it drawn that way, then all the ones on one side are one color and all the ones on the other side are the other color. Okay, and so that coloring theorem there is the one that you want to use to check if a graph is bipartite. You don't have to color it, obviously. Normally what you do is you just write like, you pick your two favorite colors, like you go like, blue, red, and then you just put like blue, red, blue, like you just do that. Rather than actually physically color it in, but coloring helps. And those are bipartite graphs. Let's see what else we can do with it. Yeah, okay. So let's actually one more special graph. So we have the complete bipartite graph, which is going to be called K. K was complete before, but now we do like an MN thing because it's going to be bipartite. So complete bipartite graph. And what it is it's going to be bipartite and it's going to have all of the edges that it can have. So the complete graph had all possible edges between vertices. This is going to have all possible edges that it could have and still be bipartite. So so basically what you do is this. So let's see. The vertex set V has two, I'll say, is partitioned, sorry, is partitioned into V1 with M vertices and V2 with N vertices. And so the idea there is, right, that's what the M and N are. They're the size of the set of vertices. So M vertices in one, N vertices in the other, and edges, one edge between every vertex in V1 and each vertex in V2. So, like as an example, we don't need a lot of examples of this, but as an example, we could do like K34. So what would K34 be? So you draw 1, 2, 3, and 1, 2, 3, 4, like that. And then all possible edges. So you connect this vertex here, 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 here. Then you move down to the next one and you go here, 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 here. And then you move down to the third one and you go here, 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 here. And there you go. That's K34. So it's complete, right? There's no more edges that you can draw. If it's going to be a simple graph with no multiple edges, um, you can't connect any of these because then it won't be bipartite. You can't connect these because then it won't be bipartite. And other than that, it has that many edges. Now, how many edges does it actually have? I think it has m times n edges, right? Because like if there's 3 over here and 4 over here, you have to go 4 edges, 4 edges, 4 edges. So 3 times 4. So looks like KMN has MN edges. All right. And that is bipartite graphs. So we're out of time. There's some applications of bipartite graphs that we're going to talk about, but we'll talk about that in the next lecture. So I think that's it for now. Talk to you guys later. Yeah, that's about it.